All right, so let's look at this problem. First example problem in trying to write a function for shear force and bending moment. Okay, what's the first thing we should notice? Look at the way the load is applied to the structure. Is that a continuous function?
Yes.
Yes, it is. Right? It's linear. So that means I can write one equation that will describe the shear force and bending moment that's valid for the entire structure. So look at the load and notice that it is continuous, no abrupt changes. So we can write one set of equations. That's good. So what's the first thing we should do? Let's investigate. I've already kind of give you an idea. Let's make a cut here, say at X. So let me go ahead and make a vertical line here. And let's look at the left side and the right side and decide which way we want to go. Let's start with the left. So what we need to get started here on the left? Well, I would need the reactions at A. It shouldn't be too hard to find. And then when I'm examining this left side free body, you'll notice that the applied load is what? Triangular. That's not so hard. We've done triangular loads before. So keep that in your memory. And now let's look at the left-hand side. So I kind of cover that up. So looking at the left-hand side, I don't need any reactions to work the left-hand side. That's an advantage. However, there's a disadvantage, which is the resulting applied load is trapezoidal. So you have to break that up into a rectangular piece and a triangular piece. And that could be an issue. Now what I'll try to do today is I'll work it both ways and we can do a little compare and contrast. Okay? So let's first start with, I'll do the left-hand side first. And in doing that, I need my reactions. So let's start by drawing a free body diagram of the whole structure. And I will assume, now I'm trying to find shear force and bending moment, right? So what's positive shear on the left-hand side, up or down? Up. Right? So I'm going to say that's positive shear at A, and I'll put positive. What about bending moment? Like this, right? So this is positive bending moment at A. I made my two assumptions. And then I'm going to come back and I'm going to replace the distributed load with the concentrated equivalent. And what should that value be? The area under the curve, right? 1/2 base times height is what? 1/2 20 times 2 is what? 20 kips, right? And where is that located from A? Yeah. Yeah.
You did a free body diagram of the whole thing.
Right.
So now why do you put in the shear and the moment about A when it's just dependent to just be an A1?
It's fixed connection. So it has both a vertical force and a moment.
Okay.
But since we're talking about shear and moment, I want to go ahead and know what my shear force and bending moment are at the beginning of the beam.
Thank you.
Okay. So this distance is 2/3 the total distance, which would be 2/3 of 20. And just for fractions, I'm going to write it as 40/3 feet. So I don't have to worry about doing a calculation right now. So far, so good? So now I'll come and I'll sum my moments at point A and set those equal to 0. Now I'm doing equilibrium, so my sign convention for equilibrium is right-hand rule. So looking at that, what kind of moment is this? It's negative. What kind of moment does the 20 kip force create about A? Also negative. And it has a moment arm of 40/3. So what is the moment at A? Now you're going to have to help me out. 800 divided by 3 is what, 266.7? Guessing.
Yeah.
So 266.7, that would be kip feet. And it came out negative, which means what? My bending moment at A is negative. Does it make sense that this structure has a negative bending moment at A? Yes or no?
Yes.
Why? Why is yes? Well, how is this structure going to deflect? It's going to come out and probably go down like that. And if you look at it, that's kind of half a frown. See that? See the frown? Half a frown? It's bending down. That's a negative bending moment. You guys don't like my frown analogy, do you? Okay, so let's go ahead and finish with the shear force. So I'm going to say up is positive, and I'm going to sum forces in the y direction. So that shear force is up, and the 20 kip force is down. So it looks like the shear at A is 20 kips. Okay? So now let's come back and look at the left side free body diagram. So I'm going to redraw this structure. And I'm going to put my values on it. Okay, first of all, I know that this force is up and equal to 20 kips. And the moment is negative. I assume positive, so the moment's actually in this direction of 266.7 kip feet. And then I have my load. Now this is a distance x, so what is the intensity of the load there at a distance x? Well, you basically just have to write this as an equation. So if I go back up here and try to write my load as a function of x, what should I get? Well, remember in general, a linear line is ax plus b. B is the y-intercept. So at x equals 0, what's my load? 0. So that should be 0. And what is the slope of this line going to be? Rise over run. So that's 20 kips per feet over 10 feet. So you get a very strange unit. In this case, it would be 1/10. And it's going to have strange units. I'll just say kip feet squared right now, but it'll work out. So that means this is just going to be x over 10. Everybody see that? So when you can check it. When x is equal to 0, what do you get? 0. When x is equal to 20, what do you get? 20 divided by 10 is 2. So it works. So far, so good? Okay, now I'm going to come to my cut edge, and I'm going to assume positive shear force and positive bending moment. Now, we never like to deal with our load, since it varies. We like to do what? A concentrated equivalent, right? So let's do the same thing that we've done before. Let's say we have a concentrated equivalent force. And what is that force? Well, it's a triangle. Area of a triangle is always 1/2 base times height. So that'll be 1/2 the base, which is x, times the height, which is x over 10. So that's going to be x squared over 20. See that? So as my position of my cut changes as a function of x, the force automatically adjusts to that. And what's the distance between the force and the cut surface here? Well, a triangle, it's always 1/3 the distance. What's the distance? So this will be x over 3. You may not have drawn a free body diagram like that in the past. That's a function of the base. But now you have. Now, for me, when you work these problems, say on the exam, That's that's half the problem right there. If this is correct, I'm going to give you half credit. Because that's really the problem. That's breaking the free body down, putting all the components on. That to me is half the problem. The rest now is just what? Apply equilibrium. So we'll do that. So we'll start by summing our moments, and we'll sum them at the cut, and we'll make sure they're equilibrium. So let's just account for everything. I'll start here on the left and work this way. So my assumed moment here is positive or negative? Using right-hand rule. Positive. What about the concentrated equivalent force? Is it creating positive or negative moment about the cut? Positive. So the force is x squared over 20, and the distance is x over 3. So just to remind you, force, distance. Then I come over here and I've got this 20 kip reaction force. Is that creating positive or negative moment about the cut? Negative. So that'd be 20 kips. And what's its moment arm? X. And then you've got the moment here at the end. Is that positive or negative with my sign convention? Positive. So what don't I know? Moment. So solve for the moment. So the moment now is going to be a function of x, and it's going to be equal to, this first term will be, I'll put the units on the outside. So it'll be x cubed over 60. I shouldn't have put that there. Well, I messed up.
Will it change signs? Put the negative sign right there. Will it change the signs on the inside? So it'll be x cubed over 60.
We'll just leave it like that.
Plus
20x plus 266.7. The minus sign will go through. I just wanted to put all the units at the end. Each of those terms is kip feet. So really the first term is negative, positive, negative, if you slide that all the way through. So that's what our equation for the moment in this beam is. Now, can we check that equation? Sure. Where do we know the moment? Well, we've calculated it here at A, and that's at x equal what? 0. So put in x equals 0. This term goes away, this term goes away, and you get negative 266.7. That's correct. Where else do you think you know the moment in this structure? What's the moment at a free end? 0. So if I put in x equal 20 here and here, hopefully this will give me 0. So you guys should check that. While you're checking that, I'll just write over here on the side that the moment at x equals 0 should equal minus 266.7, and we're thinking the moment at x equal 20 should be 0. And the first one we've already got. Yep, check that work. Somebody checking that out for me? Mr. Baker says okay, so I like that. It's good when your equation matches the things you know are true. Okay? So how do we find the shear force as a function of x? Some forces in the y direction. Make sure they're in equilibrium. I'll assume up is positive. So my shear force here is down, negative shear. My applied force is down, x squared over 20. And this reaction is up. Did I get everything? Minus shear, minus concentrated load, plus the reaction. So it looks like the shear as a function of x is equal to minus x squared over 20 plus 20. And that all has the units of kips. Now, do we know anything about the shear force? What's the shear force when x is equal to 0? Positive 20, right? So you put in x equal to 0, what do you get? Positive 20. What do you think the shear force at the free end is, at B? Probably 0, I would guess. There's nothing there to stop it from moving up and down. So this just tells us the shear force at x equal 20 is 0. And if you put an x equal 20 there, you get 0. So again, when we check our two conditions that we know, at x equals 0, it should be 20 kips. And at x equal 20, it should be 0. Both those things, check. So I'm feeling pretty good that these are right. Now some of you who think more in higher math might notice that there's a relationship between moment and shear. Think back to Calculus 1. Yeah, it looks like, right now, if I took the derivative